Okay, so for homework 4, part 1, we're going to be deriving the flow rate equations for at a steady state of two different containers, as shown, two circular containers. Connected at the bottom, and then if this is container 1 and container 2, container 2 drains off to the right. They both have inlets, and at an initial steady state, which is basically saying that the liquid height is not changing, we want to derive the equations to find the flow rates. So steady state means that these heights, H1 and H2, are not changing. And we're looking to solve for Q. So we have several different flow rates. We have Q1 in, and that's for the inlet to tank 1. We have Q2 in, which is the inlet for tank 2. We have Q12, which is the flow rate between tank 1 and tank 2. And then we have Q2, which is the flow rate of liquid leaving the second tank. We also have to take into account the cross-sectional area. So this is A12, that's cross-sectional area of the pipe, and then A2, cross-sectional area, as well as velocity of the liquid, V12 and V2, for the velocity of the liquid within the pipe. Now we know that the flow rate, Q, is equal to A times V, which is the cross-sectional area. I'm just going to write the cross area over the velocity. Okay? And so what we're looking for here and what we need to solve for, or we can see immediately using these variables that the flow rates in each of these pipes, for the first one, pipe 1 to 2, we have Q12 is just equal to A12 times V12, and Q2, the flow rate leaving Q2, is equal to A2 times V2. And then from there, we're going to use Bernoulli's equation to kind of rearrange and solve and help look for the velocity of the liquid leaving the pipe. Okay, so now we're going to look at our Bernoulli's equation for this problem. It's going to be P2 plus P1 in a row, and plus G equals 0. And then a couple things that will help us simplify this is we know that both of our containers are open to the atmosphere, therefore pressure would be equal to 0. So this whole term is just equal to 0, and we can forget about this. And also, our V1, our initial velocity, is we're not concerned about that because of the opening and the tops of both of the tanks is too large to consider it. So this is also going to be equal to 0. And if we drop this down, we have our G term, which is equal to negative V2 over 2. Sorry, this whole thing was squared, so it is V2 squared over 2. And then from there, we're going to solve for velocity, or V2. And when we do that, we get V2 is equal to 2g delta z. So our change in height times 2g, square root 2g of the change in height, the liquid level, right? So that was our h values in the previous board. So now we're going to separate this out into the velocity equation for pipe 1, 2, and then our velocity equation for pipe 2. So if we look at our velocity equation for pipe 1, 2, so V1, 2, right, it's going to be same thing, 2g, and then delta z, we go from h1, the height in the first tank, to the height in the second tank. And for this problem, we do know that the height in the second tank is less, so we do h1 minus h2. H1 minus h2. And then for our V2 is a little bit simpler. It's the height in the second tank, so 2g, and our delta H is just the height in the second tank, and then to 0 because we're draining directly from that second tank. So it's just going to be H2 minus 0, which is H2. So now we're going to be able to rearrange these equations and then eventually just get our flow rate equations. So where we go from here is we take the velocity equations that we just got, and we're going to plug them back into the two different flow rate equations. All right, so Q12 is A12 times V12, which we just got. So that's 2g h1 minus h2, and our Q2 equals A2 times 2g h2. And if we think about finding these versus the relationship to the flow rate coming in, we can mess around with these a little bit and actually just solve for both flow rates coming in, both in tank 1 and into tank 2. So if we think our Q1 in, our flow rate of liquid coming into tank 1 has to be at steady state, right, because the liquid height isn't changing. It has to be the same as the liquid leaving tank 1. So basically Q1 in is equal to Q12. And also we can rearrange that, basically 0 is equal to Q1 in minus Q12. And then from there, since we also aren't concerned with the area for the flow rate coming in, we can do Q1 in is just equal to 2g h1 minus h2. And this does depend on the sign of this h1, h2. But we don't have to worry about that for this first part. And then same thing over here, a little bit more complicated, but basically our Q2 in is our Q2 in plus, so our liquid coming into the tank through the top is not the only amount coming into tank 2. We also have our Q12, the liquid coming from tank 1 to tank 2. So we take, if we imagine at steady state, the amount of liquid coming in from the inlet in tank 2 plus the pipe between the two tanks, so Q12, minus Q2, which is the liquid leaving, these have to be equal, right? So basically Q2 is equal to these two combined. And if we rearrange, we can just simply get that our Q2 in, because this is our Q1 in, is equal to 2G H1 minus H2, and then minus 2GH2. And so these two equations are the flow rates for liquid entering both tanks. And then now we're going to look at differential equations in order to solve for the change in flow and over time. Alright, so now we're looking at a differential equation to kind of look at this as a change over time, a change in volume over a change in time, right? So if we think about our tank 1 as Q1 in minus Q1, 2. If this isn't at a steady state, right, normally this would equal 0. But if this is not at steady state and that volume is constantly changing, we can look at this as dV over dt, right, a change in volume over change in time. And if we kind of expand a little bit on this, we have dV over dt is equal to Q1 in minus, and we'll replace our Q12 here for A12, and then, so this is Q12, right? 2G H1 minus H2. And now since our heights are no longer at steady state, we can take into account whether or not the height of the second liquid in the second tank is actually greater than the height in the first tank. Because this whole time we've been writing our equations as if the height in the second tank, that the flow is going from the first tank to the second tank. But actually, if our liquid level in our second tank is higher, it's not going to do that. So we can look at that. We can account for that just in our equation. Q1 in minus, and then we'll do plus or minus A12, and then 2G H1 minus H2. That's sloppy, but so this will actually be the sine function, not trig, but sine function. So it'll be sine of this H1 minus H2. So if H2 is greater than H1, that'll be negative, and our equation will look a little different. And we'll get to that in the code. So right now, I'm just going to quickly erase and do the same thing for our second tank, just so you can see the difference. So our equation for the second tank is just a little bit longer, but it's still going to be the change in volume over the change in time. And we know that it's, right, Q2 in plus the stuff coming from tank 1, so Q12, and that's minus Q2, usually equal to 0. Again, we're saying that our volume could change over time. Then we'll substitute these in, dV over dt equals Q2 in plus Q12, A12, 2G H1 minus H2, and minus A2, and then 2G H2. And again, if we want to look at it, taking into account that H2 could in fact be at a higher level, we'll do the sine function of H1 minus H2, so that if it is greater, then we're looking at a different equation here. Alright, so now we're going to move on. I'll be back after I erase this real quick. So as of now, we have equations for our change in volume over time, our dv dt. But we're going to basically, we need, for the purposes of this problem, we're looking for the change in height over the change in time. And so the relationship there is dv over dt is equal to dh over dt times the cross-sectional area. And what the cross-sectional area is basically just this space in here. The change in height, we're looking at that cross-sectional area. And also, if basically to simplify this further, our dh dt is equal to dv dt all over cross-sectional area. And so I'm gonna blow this up real quick, actually, so that you can get a better idea of where we're going. So if we have our radius here, r, and then this is going to be h t minus r, h of t over here. I'll just draw a radius here too, or sorry, the radius here, and then this is R1 t right there. And so basically we can derive out an equation for this using the Pythagorean theorem. This right here is ht minus r. This is ht, and then minus a radius here gives us the height between the radius and our h of t, our liquid height at a certain time. Right, so Pythagorean theorem, we get r squared, which is equal to h of t minus r, that's squared, minus r of the cross-sectional area, t squared. And then if we just remember that our cross-sectional area is pi r squared, we can simplify a little bit, and we get, I'll write it over here, is equal to pi sorry about that. R squared minus h minus r squared. And now from here, we'll be able to solve for the differential equation. So if we remember this equation, dh over dt is equal to dv dt over the cross-sectional area. We actually know now both the cross-sectional area and our dv dt terms for both tanks. So if we take our first tank here, dh1 over dt, we have that q1 in minus the sine function of H1 minus H2 times A12, and then 2G H1 minus H2, and that is over what we just solved for the cross-section area, so pi R1 squared minus R1 minus H squared. So this is our differential equation that we need to solve for the height of liquid over time in the first tank. And then our second one is a little bit longer. I'm going to try to fit it all in one line. dH2 over dt is equal to Q2 in plus sine function. I already can tell I'm going to run out of room. H1 minus H2. Forgive me if this is a little small, but I'll be sure to say what I'm writing here. Our A12, 2G H1 minus H2, and that is then subtract our A2 and then 2G H2. Again, this is our flow rate leaving the entire system, or pipe 2, and then over the same cross-sectional area, R2 squared minus R minus H squared. And so these we'll use in our code, and with some values that we know to solve for the flow rates between pipes and out of the system. Thank you.